Welcome friends. So, as we said in the previous class that we are going to take up some practice problems on natural purification aspects or the estimation of BOD, DO, COD in the system. So, let's discuss some of the problems, how these are solved. Okay. So, the first problem is on dilution, which says that sewage of a town is to be discharged into a river stream. The quantity of sewage produced per day is 9 million liters and its BOD is 350 milligram per liter. So, we have been given the discharge of the sewage. So, flow rate of the sewage is given as 9 million liters per day, 9 MLD. Okay. And the BOD of the sewage is also given as 350 milligram per liter. Now, if the discharge in the river is 250 liters per second, so we have a discharge in the river as 250 liters per second and the BOD is 6 milligram per liter, BOD of river is 6 milligram per liter. Then find out the BOD of the diluted water. Okay. So, you have a river where there is a sewage stream from the town is getting discharged, and as we discussed the concept of dilution based on the basic mass balance principle. So, the concentration, let us say this is your sewage, so flow in the sewage and BOD in the sewage. This is your river, so flow in the river is QR and BOD in the river is, let us say, BODR. So, at this mixing point post downstream, the total flow in the river will be QR plus QS as this thing, and say the BOD is, let us say, BOD of mixed, or okay. So, QM is equal to QR plus QS and we need to determine the mixed BOD. So, BOD of the mixed will be equal to BOD of the sewage into flow of the sewage plus BOD of the river into flow in the river divided by flow in the or mixed flow. So, which is your QR plus QS. However, one needs to see that the units are appropriate. This is milligram per liter, fine, this is milligram per liter, fine, this is liter per second and this is million liters per day. So, we need to convert this either to million liters per day or we need to convert this as liters per second, right. So, if you want to convert this to, let us say, million liter per day, how we are going to convert that flow in the river? So, we have 250 liters per second. So, that means you multiply it with 60, we get 250 into 60 liters per minute. You further multiply it with 60, you get per hour, and you further multiply it with 24, you get per day. So, this much liters per day, and you divide it by 6 or you further multiply it with the 10 to the power minus 6, you get million liters per day. Okay. So, that way we can estimate, or we can convert similarly this into the liter per second. So, we have 9 into 10 to the power 6 liters per day and there is 24 hours in a day. So, we let us divide it by 24 and then this becomes per hour, then into 60 this becomes per minute, and further into 60 this becomes per second. So, 9 into 10 to the power 6 divided by 24 into 60 into 60. So, either we use this and this or we use this and this. Okay. So, and this is available. So, we can multiply that and simply get the factor. So, it will be, your solution is going to be like this. So, the sewage discharge, if we try to convert in liter per second as we discussed, this into 10 to the power 6 into 24 into 60 into 60. So, this gives 104.167, this is 350, this is already 200. So, now these units are same and we can use this as 350 into this discharge, 6 BOD into the discharge in the river, and then total discharge. So, this gives approximately 124 milligram per liter of the BOD. Okay. So, river BOD, initial BOD from 6, it turns to 124 after this waste stream is discharged into the river. So, that is one simple problem of the dilution. Okay. Now, let us take another problem on DO deficit. Okay. So, a city discharges say 1500 liters per second of sewage into a stream whose minimum rate of flow is 600 liters per second. Okay. So, this question you have again a sewer line coming in, there is flow rate is given. Okay. So, of sewage, flow rate of river is also given. Okay. The temperature of the sewage as well as water is 20 degree. So, temperature of both is 20 degree. So, if it is both 20 degree, the mixture will also remain at 20 degree. The DO content of the sewage is 0. So, the dissolved oxygen here is 0 and the stream is 90% of the saturation value. The DO here, the dissolved oxygen of the river is 0.9 times of the DO saturation value. Okay. Assume the instantaneous mixing of the sewage in the stream and we need to find the initial DO deficit. Okay. So, what is the DO deficit? Now, we know that DO deficit, which typically we note by D, is equal to DO saturation level DO minus the existing DO at any given point of time t or whatsoever. So, remember we had a table what are the when we were discussing the DO as a parameter. So, what are the different values of the dissolved oxygen at different temperature, the saturation values. So, DO saturation at 20 degree Celsius is 9.17, which is one of the pretty common temperature which is given. So, we know that DO at 20 degree Celsius, DO saturation at 20 degree Celsius is 9.17, and in order to find the DO deficit we need 9.17 we know, and then we need to find what is the dissolved oxygen of the mix, and that way we can get the deficit. And dissolved oxygen of the mix we can get from the dilution concept, okay, which we just earlier discussed. Okay. So, DO of river, existing DO of river is 0.9 times of 9.17. Okay. So, that is the existing DO, DOR, and DO of the sewage is 0. So, we have all these values, and similar to the earlier problem, we can first do a dilution, we can first do a mass balance for that and determine. So, this becomes 8.25 milligram per liter, okay, the DO of the stream. So, DO of the stream into flow in the stream, DO of the sewage into flow in the sewage divided by flow in the sewage plus flow in the stream gives us a DO of 6.6 milligram per liter, and the initial DO deficit is saturation DO minus DO of the mix. So, that gives us 2.57 milligram per liter. So, that way simply we can actually determine what is the deficit of the dissolved oxygen. Okay. These are the simple problems. Now, let us take another practice problem on BOD estimation. Okay. So, BOD estimation is particularly from problem perspective is actually one of the topics which is often asked in several competitive exams as well. So, particularly those preparing for GATE or those kind of exams or ES, you are likely to see at least one question or so on this particular topic. Okay. So, this is often like almost every year there will be some questions from the this BOD part. Okay. Questions are simple, they are not very complicated questions. So, let us see the this question is from the GATE paper of the civil engineering of this year itself. Okay. The ultimate BOD of wastewater sample is estimated at 87% of COD. The COD of wastewater is 300 milligram per liter. So, we have been given the COD which is 300 milligram per liter, and the ultimate BOD or the L0 is 87% of this. So, 0.87 into 300 will give us the L0 value. So, straightforward, the L0 value is given. Considering first order BOD reaction rate constant at natural log, means at E base, is 0.23. So, K D is given as 0.23 per day, okay, and the temperature coefficient is also given. So, temperature coefficient, if you recall, the rate of your deoxygenation or this thing are dependent on the temperature coefficient. So, if we want to determine the Kd value at say at temperature T, we normally know at Kd value at say any given temperature at 20 degree we know. So, it will be Kd 20 times this value temperature coefficient theta to the power T minus 20. Okay. So, that way we can actually determine the Kd value at appropriate or given temperature. So, here temperature coefficient is given and it asked what will be the BOD value in milligram per liter after 3 days of incubation at 27 degrees Celsius for this wastewater. So, the time period is given to us as 3 days and incubation temperature is given as 27 degrees Celsius. So, we know the L0 value, right, and if the discussion that we had in the previous lecture, you know that the BOD exerted, which is actually BOD at consumed or demand. So, like we said that BOD at any time t is equal to your L0 1 minus e to the power minus Kd times t. Okay. So, this expression we can directly use. So, for say if we want to determine after 3 days of incubation, means how much BOD has consumed, we are not talking about the left in the system, BOD left in the system, BOD exerted, that is what the 3 day BOD means. So, BOD 3 is L0 1 minus e to the power minus Kd at 27 degrees Celsius, the temperature which is given to us, into 3. L0 value is can be taken from here. The Kd value can be estimated at this temperature from this. So, the theta is given to us and temperature here is 27 degrees Celsius. Okay. So, we know the temperature, we know the value of theta, and that way we can determine, and T is also given to us. So, we can actually get the value of the desired value of the this thing. So, the ultimate BOD becomes 0.87 into 300, that is equal to 261, okay, and K20 is given to us. K at T degree temperature is K20 minus theta to the power T minus 20. So, theta to the power 7, and this gives us 0.317 per day as the value of K. Okay. So, as we said, it will be BOD at time t will be L0 1 minus e to the power minus Kt into t. So, L0 is 261 and K at 27 degrees Celsius is this value which we have estimated, time is 3. So, we get this number as 0.614 and the total 3 day BOD or 3 day exerted BOD is 160.254 milligram per liter. So, that way we can estimate the BOD, or how the BOD is there present in the system. Let us take another problem on BOD rate constant estimation. Okay. So, how we can estimate the rate constant of BOD. This is a problem from GATE Civil Engineering of 2016 paper. So, it says that for a wastewater sample, the 3-day BOD at incubation temperature of 20 degrees Celsius is estimated at as 200 milligram per liter. Taking the value of the first order BOD reaction rate constant is given to us. So, K value, the K value here is given to us 0.22 per day. Okay. The 5-day BOD of the wastewater at incubation temperature 20 degrees Celsius is to be estimated. Okay. So, we have been given the value of K, we have been given the BOD rate, we have been given the BOD value of 3. So, we know that BOD 3 is equal to L0 1 minus e to the power Kd into 3 time 3 days, right. So, for this we have been given this value and we have been given this rate constant value. So, only unknown is L0, and from this we can determine L0, and then for BOD 5 we know that again it will be L0 1 minus e to the power minus Kd times T, and T here is 5 for BOD 5. So, for this now we know the L0 value from here. So, this is given to us, we know the Kd value given to us, 5 is already there. So, we can determine what is going to be the BOD 5, okay. Simple problem. So, it will be, the solution will be like this. So, at 3 days BOD is 200 milligram per liter, rate is given to us. So, BOD T is this, we know. So, BOD at 3 days, after 3 days is 200 and L0 e to the power minus 3. So, this gives us the ultimate BOD as 414 milligram per liter, and then BOD after 5 days at 20 degrees Celsius, which is your BOD 5, is L0 1 minus e to the power minus K 20 into 5, and this gives us the number as 276.2 milligram per liter. So, that becomes the BOD 5. Okay. So, you see that BOD 3 was 200, BOD 5 was more, and ultimate BOD is even higher. So, that is how the BOD estimation happens. BOD exerted, if you see the oxygen demand exerted. So, initially as you see day 1, day 2, day 3, day 4, day 5, okay, it may further increase actually that way around. So, it is lesser on day 3, higher on day 5, and ultimate BOD is eventually, which is the maximum demand, maximum oxygen demand it can exert, will be the highest. Okay. So, eventually if you extend this curve for further longer and longer, it will get static around this value. So, that is what the ultimate biological oxygen demand is. This is another question on BOD estimation. We have two waste streams A and B having identical ultimate BOD and are getting mixed to form another stream C. So, there are two different streams, there is, let us say this is stream A, this is stream B, and they are mixing and forming another stream C. Okay. The ultimate BOD or L0 for both the streams are same, they are having identical ultimate BOD. So, if this is same and they are getting mixed, so ultimate BOD of stream C will also be same. Okay. We can just apply simple mass balance also. So, let us say flow here is QA, flow here is QB, and flow here is QC, which is equal to QA plus QB. So, because it is the same value L0 into QA plus L0 into QB divided by QA plus QB, L0 is common from the top. So, this become QA plus QB divided by QA plus QB. which gets cancelled, equal to L0. Okay. So, that is the BOD over here. The temperature of the stream A is 20 degrees Celsius, temperature here is 20 degrees Celsius, and the temperature of stream C is 10 degrees Celsius. So, here the temperature is different. Okay. It gives that the 5-day BOD of stream A at 20 degrees Celsius is 50 milligram per liter. So, BOD 5 here is 50 milligram per liter of stream A. Okay. The BOD rate constant at base 10 is 20 at 20 degrees Celsius is 0.115. So, KD at base 10 is 0.115 per day. The temperature coefficient theta is this 0.135. So, we need to determine the 5-day BOD for stream C, which is at 10 degrees Celsius. This is a question from the last year's GATE of the civil engineering. Okay. So, what we can do, like if you see the total information provided in the system, okay, for stream A we have been given the 5-day BOD and we have been given the BOD rate constant also. Okay. So, we know that BOD 5 is equal to L0 1 minus e to the power minus KD into T, that is when it is exponential base, when KD is given at 10 base. So, this E becomes 10. Okay. So, this equation will be applicable because this is given at base 10 and not at base E, right. So, this becomes our BOD equation for this. Now, here KD at the stream A is at 20 degrees Celsius, okay, and KD is given also at 20 degrees Celsius. So, that is fine. So, we can basically use this. So, this value is 50. Okay, this value is not known to us, L0, which we need to determine. 1 minus 10 to the power, this value is 0.115 per day and it is a 5-day BOD. So, this value is 5 into 5. So, we know this number, only thing is L0. So, we can determine L0 from here, and since the A and B are having identical L0, the L0 of the C is also same. So, we know the L0 value for stream C also. So, we know L0 value for, basically it is same for all 3 streams. So, stream A, B and C, we know L0 values for all the streams now. The next thing is that stream C is at 20 degrees Celsius. So, we need to determine the KD value at 20 degrees Celsius. KD at 20 will be equal to at 10 degrees Celsius. So, KD at 10 will be equal to KD at 20 degrees Celsius and into theta to the power T minus 20. Theta is given to us, T is 10 here. So, that way we can estimate the new value of KD, and then for stream C again we have the BOD 5 is equal to L0. Now, we know the L0 from here, and 1 minus 10 to the power minus KD at 10 degrees Celsius. So, we know now KD at 10 degrees Celsius from here into 5. Okay. So, we know all these things and we can estimate the BOD 5 value. So, that is how we can actually solve this. So, if we see the solution for stream A, we have 5-day BOD as 50 milligram per liter given, rate constant given, theta value given. So, BOD this thing, and we can get the L0 value considering at base 10, and since the BOD remains the same. So, C will also have the same ultimate BOD. So, for stream C, first the BOD rate constant at temperature 10 degrees Celsius. So, K20 into theta, which is given to us to the power 10 minus 20. So, this becomes our the 10 degree Celsius rate constant, and then 5-day BOD for stream C at 10 degree Celsius will be L01 minus e to the power K10, which we have estimated here, and this gives us 21.22 milligram per liter. So, with the same ultimate BOD, this is interesting to see, with the same ultimate BOD, one of the stream which is at higher temperature is exerting an oxygen demand of 68.12. Same existing BOD means the initial organic matter, amount of initial organic matter is the same in both the streams. One is exerting a 5-day oxygen demand of 68.12 milligram per liter, while another is exerting a 5-day oxygen demand of just 21.22 milligram per liter. The difference being that the stream C is 10 degree cooler as opposed to the stream B, which as opposed to stream A, which is at actually 20 degree Celsius, right. So, you can clearly see the effect of temperature over here. With the lower temperature, the biological activities has reduced and the exerted demand of oxygen has reduced. Organic matter is still the same, but exerted demand in the 5-day has actually decreased down, because the rate of the decay has slowed down. So, you see the rate of decay here is 0.115 per day, while rate of decay here is 0.03. So, almost 1 order of magnitude lower, okay, almost 5 times lower than this, and that results in the reduction of the oxygen demand as well, or biological oxygen demand as well. Okay. So, that is how it can actually be like solved. So, problems are simple if you see, just one needs to understand the basic concept, okay, and these are quite popular problems for exams. There is another problem from again GATE of 2016. There is a 2-day and a 4-day BOD values are given of sample 100 milligram per liter and 155 milligram per liter, and we need to determine the rate constant. So, assuming that these values are at same temperature, okay, because we have to consider that the temperature is not changing. So, a 2-day BOD value means BOD exerted in 2-day, BOD 2 is L0 1 minus e to the power minus Kd into 2, and your 4-day BOD value BOD 4 is L0 1 minus e to the power minus Kd into 4, right. So, we have been given these two values, but we have not been given, neither have been given the ultimate BOD and nor have been given the rates. Okay. So, we have two equations, equation 1 and equation 2 that way, and two unknowns, or one unknown is L0 that we do not know, and another unknown is the Kd that we do not know, and that is Kd is the one that we need to determine. So, we can divide these two equations, let us say. So, if you divide these two equations, so we get BOD 2 by BOD 4, or other way also we can divide BOD 4 by BOD 2, does not matter. L0 1 minus e to the power minus Kd into 2 divided by L0 1 minus e to the power minus Kd into 4. L0 gets cancelled, okay. This number is known to us, and now the only unknown that remains is the Kd, and we can determine the Kd from here that way, okay. So, it is a pretty simple problem that way, one can see that. So, BOD for 2-day, BOD for 4-day, okay, and then if we take a ratio, we get 100 by 155 as this number, and we can easily solve this then and get a value of K, which is coming out to be close to 0.3 per day. So, that is how we can estimate the rate constant, okay. So, these are some of the problems, okay, and we will conclude this discussion here, okay, and in the next class we will start. So far what we have discussed actually in this week was practically onto the natural systems. So, when waste is introduced in the nature, what happens, how it happens, but now we will move towards the engineered systems. So, what happens when we try, or how we can conceptualize some engineering device for the treatment purpose. So, we will have those kind of discussions from the next class onwards. Thank you.